In this video, we're looking at the concept of work, specifically how we would define it in physics, which is becoming a theme that we define words differently and use them differently in physics and I guess science in general than we do in everyday life. We want to understand the connection between work and energy as our goal of all of this. We're going to start with some definitions, and these definitions may be not that satisfying right now. Energy, we define, is the ability to do work. And when work is done, energy is transferred or transformed from one form to another or from one object to another. We learn about different types of energy, and we derive them from the amount of work required to give something that energy. Create is a little bit of a weird word here because you probably heard energy can never be created or destroyed, but if it comes from some other source and gets turned into another, that's kind of what we're doing there. So we start with the simplest form of work done by a constant force. Work is defined as the dot product between a force vector, and a displacement vector. So if you apply a force and the object moves through some displacement, you have work done. The units are newtons times meters, kilograms, meters squared per second squared, joules, which is one of the many units we use for energy, and it is our SI unit based on the KMS, kilograms, meters, and seconds system. It's spelled Joule, and it is given a capital J as a system. You may also hear about foot-pounds. That's the sort of English imperial non-SI unit. It is a scalar. This is energy. This is work. There is no direction involved. There is a direction for force and a direction for displacement, but because we are computing work by a dot product, we get a scalar. It can be positive, it can be negative. More on what that means as we go along. So that's if the work is done by a constant force. But what if the force is not constant? Well, then we end up having to do something else. We have to talk about the work done by a force over little displacements, where either the displacement is simple and the force is changing, or perhaps it's a constant force, but your displacement path is not simple. In either case, you're taking little intervals of displacement and seeing how much force was applied for each of those. And if the force is changing, you really need to integrate. And so what that looks like is this. The work is the integral of F dot dr, where instead of a delta r, we collapse that delta down to a really, really tiny, arbitrarily small interval. Now, I will pause right here and say, what I say about integration in this video and in this unit, and really in this entire course, should be taken as this is how we use integration in this course to give us useful answers about things. We're going to use it like this to sum up lots of little pieces, and we'll use it in a couple of different ways. But we are not saying that we are teaching you the concept of integration in depth. For that, look to your calculus and math courses. So this is the equation that's on the APC equation sheet, and that's useful to have. You can also use graphical methods, right? If you were able to plot the force over position, if you imagine using one of our force measurement devices, a force probe, and we're able to say, oh, it's this far away. And we can look at this. We may do a demo of this in class. If you could find the amount of work done in each of those little segments, this is, a method we use to approximate integrals, as well as you keep making these little rectangles. You could also use trapezoids. There's different approximation methods, but what you get is an area here under the curve, distance or displacement times force that we can use. So in order to actually do these calculations, you have to answer two questions first. What object do we care about? Because we're talking about forces, and forces are always on a particular object. And then specifically, we have to talk about which force we care about, because each force could do work on a given object. And I'm trying to emphasize those words. A force does work on an object as it is applied. So for constant forces and simple situations, work is F dot delta R. And so we can look at this example here. A crate is pulled across the floor at a constant velocity. Calculate the work done by each of the forces and by the net force, because you can calculate the work done by individual forces, and you can also calculate the work done by the net force. We call that the net work. More on that in a second. If I have this particular situation, I've got a force of gravity pulling down, of course, an applied force at an angle. There's a normal force and a force of kinetic friction. This is a constant velocity situation, which means the net force is 0. So once I know that the applied force is 100 newtons and the weight is 100 newtons, I can fill in the rest of the forces. That's kind of a Newton's first law situation problem. Then we go to actually calculating these values. Well, what is the work done by the applied force? Well, that's 100 newtons times 10 meters times the cosine of 30 degrees, because that's how we use the dot product with magnitudes and angles, giving us about 870 positive joules of work. The work done by the normal force is going to be 50 newtons, 10 meters, but it's the cosine of 90 degrees because the angle between the force vector, which is vertical, and the displacement vector, which is horizontal, is 90, giving us 0 joules of work done by the normal force. And hopefully that will make a little bit of sense based on the definition of work. It's a force doing work on an object as it moves through a distance. And there's no distance moved up. So that's why we get that. For the force of gravity, it's a very similar thing. And for the same reason, we get 0 joules of work because it's at a 90-degree angle. Remember, 0 work is done, or the result of a dot product is 0 when we're dealing with 90-degree angles. The kinetic friction is at an angle of 180 degrees. It is opposite the direction of displacement. So we will end up with negative work, negative 870 joules of work. We could do two things. We could either sum up the whole column, positive 870 plus 0 minus 870 to get 0 joules of work, or we can calculate the net work is the net force times the displacement times the cosine of the angle between them. There is no angle here because the work is 0 and we get 0 joules. So we can add them up either way. So normally we would do this as a partner, and we'll do this in class on packet page 5. So you can look ahead at that and give some of your ideas on how work begins. But here's a problem that we can consider. A 2-kilogram block falls 5 meters. How much work does the force of gravity do as it falls? Well, this is a very simple case. It's a free fall problem. So the only work is done, the only force on it is the force of gravity, and it happens to be in the direction of the displacement down. So we get Fg times R times the cosine of the angle. We get 100 joules of work. Positive, because gravity is in the direction of the displacement. So what about this? You lower a jug of milk a distance of 1 meter onto the table at constant speed. How much work do you do? Well, the displacement is down, but you are applying an upward force. You're applying, you could call it an applied force, or think of your hand as a surface, a normal force. That's the cosine of the angle, 180 degrees, gives us negative 40 joules of work because you are applying a force up as the jug lowers down. And you might say, why am I applying a force up here? Well, if you weren't, it would be in free fall. The jug would just be being pulled down by gravity and it would free fall. What is the net work on the milk? Well, this is interesting. If it's going at constant speed, then the net force is 0, and therefore the net work is 0. And this is leading into something we call the work kinetic energy theorem, which we'll talk about in our next video, where we can talk about useful things that we can learn from understanding how much net work is done.